Working of electric bell. Let us study how an electric bell works to produce sound. In an electric bell, the terminals T1 and T2 are connected to a battery through a push-button switch. When the push-button switch is pressed, electric current flows from the dry cell to the electromagnet and then to the contact screw and finally to terminal T2 and again to the dry cell. Thus, the electric circuit is completed. When the electric current flows through the bell, the following effects take place. Electromagnet gets activated and pulls the soft iron armature strongly towards itself. The spring connecting the armature and the stud S gets under tension. The hammer strikes against the gong, which produces sound. The electric current flowing in the circuit breaks at the contact points, but the armature and hammer continue moving towards the electromagnet due to inertia of motion. As the electric circuit breaks, the electromagnet gets demagnetized. Thus, it cannot hold the armature. At this moment, the spring, which is under tension, brings the armature to its original position. As the armature returns to the original position, the electrical contact is re-established and electric current flows through the circuit. Thus, the armature is again attracted towards the electromagnet. In this way, a rapid make and break of electric contact takes place and the hammer hits against the gong, producing a ringing sound.
An electric motor is a machine that uses electric energy to produce motion. Electric motors operate a variety of devices, from vacuum cleaners in the home to windshield wipers in the automobile to conveyor belts in the factory. All electric motors that produce rotation work in essentially the same way as a direct current series motor, which is commonly used to drive electric railroad cars. Current flows through a wire to a block of graphite called a brush. The brush transmits current to the commutator, which consists of 2 or more semicircular split rings. The commutator is connected to a large coil of wire called the armature and to the output shaft. Current flows from the commutator through the armature, then back to the commutator. Current then flows through another brush to 1 or more electromagnets, each made up of a wire coil wrapped around a piece of iron. This flow of current through the magnet's coil produces a field of magnetism. The field has a north pole and a south pole, as shown in this simplified picture. The current in the armature, one loop of which is shown, interacts with the magnetic field in the coil, producing motion. The direction of this motion depends upon the directions of the field and the current. The split ring of the commutator interacts with the brush to keep the armature current flowing in the same direction relative to the field. Thus, the loop and the output shaft continue to rotate in the same direction.
Dynamo know about. A dynamo is an electrical generator that produces direct current with the use of a commutator. Dynamos were the first electrical generators capable of delivering power for industry, and the foundation upon which many other later electric power conversion devices were based, including the electric motor, the alternating current alternator, and the rotary converter. The first dynamo based on Faraday's principles was built in 1832 by Hippolyte Pixay, a French instrument maker. It used a permanent magnet which was rotated by a crank. The spinning magnet was positioned so that its north and south poles passed by a piece of iron wrapped with insulated wire. This early design had a problem. The electric current it produced consisted of a series of spikes or pulses of current, separated by none at all, resulting in a low average power output. The dynamo was the first electrical generator capable of delivering power for industry. The modern dynamo, fit for use in industrial applications. The dynamo electric machine employed self-powering electromagnetic field coils rather than permanent magnets to create the stator field. The use of electromagnets rather than permanent magnets greatly increased the power output of a dynamo and enabled high power generation for the first time. This invention led directly to the first major industrial uses of electricity. The electric dynamo uses rotating coils of wire and magnetic fields to convert mechanical rotation into a pulsing direct electric current through Faraday's law of induction. A dynamo machine consists of a stationary structure, called the stator, which provides a constant magnetic field, and a set of rotating windings called the armature which turn within that field. The motion of the wire within the magnetic field causes the field to push on the electrons in the metal, creating an electric current in the wire. Thanks for watching this video. Please subscribe the channel for more related videos.
Transformers are composed of an iron core ring wrapped in coils. One coil is connected to an AC input voltage and is called the primary coil. The other coil is connected to an output circuit with a load resistance and is called the secondary coil. The two coils are well insulated from each other and do not form a physical electrical connection. This gives a transformer its unique electricity-altering properties. Transformers can either step up or step down a voltage. In a step-down transformer, the number of turns in the primary coil is greater than the number of turns in the secondary coil. In a step-up transformer, the number of turns in the secondary coil is greater than the number of turns in the primary coil. The constantly changing current driven by an alternating voltage source induces a changing magnetic field in the core of the transformer. The magnetic field created by the alternating current in the primary coil generates the flux in the transformer core. The secondary coil converts the flux back into current flow and produces a voltage at the load or resistance in the secondary circuit. If there are fewer coil turns on the secondary than on the primary, this is called a step-down transformer. The resulting voltage in the secondary circuit will be less than the primary. In this example, we have 20 turns on the primary coil and 10 turns on the secondary coil. To determine the decrease in voltage occurring in this step-down transformer, we can use a simple ratio formula. This formula simply states that the secondary voltage to primary voltage ratio is the same as the secondary coil to primary coil turn ratio. Rearranging the formula and then dividing 10 turns by 20 turns, we get 0.5 multiplied by 120 V. This results in a calculated step-down voltage of 60 volts.